Hello everyone, I hope all of you are doing well. We will be solving a problem on rectilinear particle kinematics, and this will be a situation with a constant acceleration for the particle. Okay, so here is the problem that we are going to be solving. So problem. So in this problem I have an incline that is fixed at a particular angle with respect to the horizontal. The angle is not very important because we are told that whatever particle is doing its business is traveling along this incline in a straight line manner. Okay, but for the sake of completeness, here is the angle. So I have a particle which I'm going to draw in the form of a ball. Okay, so here is a ball. Okay, and this is starting at the location, let's call it as A, and you're told that the ball is given an initial velocity as it starts along the incline in the following direction. Okay, so VA is 4 meters per second. As the ball travels along the incline, it is subjected to a constant downward acceleration in the direction of the incline, and the magnitude of that is given to us as follows. Okay, so as the ball travels up, there is an acceleration that this ball is subjected to, which is pointing down the incline. This is 0.25 g, where g is acceleration due to gravity, and g is 9.8 meters per second square. This is acceleration due to gravity. All right, so the things that are given to us in this problem. Okay, the initial velocity, of the particle, and that is v suffix a, which is 4 meters per second, and I'm going to draw it using this particular arrow here, which says that it is pointed up the incline. Okay, and then you're told that the acceleration of the particle is a is 0.25 g. This is the magnitude of that, and the direction of this acceleration is always pointed down the incline. Okay, so this is up the incline, and this is down the incline. Okay, what are the things that we need to find? To find the maximum distance traveled by the ball along the incline, the maximum distance traveled by the ball along the incline, along the incline before it starts returning back. Okay, back to A. Okay, and the other thing is we also need to find the time taken by the ball to travel this maximum distance. Okay, find the time taken to travel this maximum distance. All right, so these are the things that are given to us, and I just want to underline the things that are given and the things that we need to find. Okay, now one of the important things is that the acceleration of the particle is a constant acceleration, right? Which means that we have to make use of this information and try to come up with the relationship between the acceleration and the velocity and the distance traveled, okay, by means of using the particle kinematics relationships, which are the differential relations between the velocity and acceleration and so on. So I'm going to do that first, and then we will dig into the problem and complete the problem. Okay, all right, so the first thing I'm going to do is obtain the relationship between velocity acceleration and distance traveled for the case of the constant acceleration problem. Okay, for a constant acceleration. Okay, so my acceleration a is a constant, so given acceleration a is a constant, and I'm going to call this as a suffix c. Okay, then we know, okay, the following relationships from particle kinematics. A is dv by dt. Okay, that's one thing that we know. The second thing that we know is that v is ds by dt, where s is the distance traveled on the straight line path. And then the third thing that we know, which is from the chain rule of differentiation that we used in one of our concept talks or lectures, is that we have a as v dv over ds. Okay, so these are the things that we know. Okay, and I'm going to underline some of these things. I always keep losing my colors. Okay, so these are things that are given to us and things that we know from basic particle kinematics. So I'm going to start off with the first expression here. So first expression a is dv by dt, which means that if I cross multiply, I get dv is a times dt, but acceleration a is a constant, which means that I can say that dv is ac times dt. Now I'm going to integrate it on both sides. I'm going to integrate from an initial velocity v0 to some velocity at some point in time v, which means that I'm going to integrate this side from an initial time t0 to some point in time t. Okay, now since ac is a constant, the integration is fairly straightforward, so I'm going to write down the result. Okay, so this gives us one of the key results. If I do the integration on one side, I get v minus v0, and then this is going to be ac times t minus t0, which means that the first equation I get from the constant acceleration case is v0 plus ac times t minus t0, and I'm going to put a box on this equation. This is a fairly important one, and something that you need not remember, because this is something you can always derive, as we just did here. Okay, now second thing that I'm going to do is this. Okay, I have a relationship between v and time t, and v0 is the initial velocity. Okay, so I can make a note of it here. V0 is the initial velocity, and t0 is the initial time. Okay, and this is v at some point in time t. Okay, v is the velocity at some time t. Okay, now I bring out the other one, which is v is ds by dt, right? Which means if I cross multiply, I can say ds is v times dt, but I already have a relationship for v in terms of a function of time, right, which is the first box, which means if I do the substitution, then I can say ds is v0 plus ac times t minus t0 dt. And all I have to do is if I have to find an expression for the distance traveled, then I have to integrate this from a starting distance s0 to some distance s at some point in time t. This will have to be integrated because the integrand is a function of time. This has to be integrated from time t0 all the way to some time t here. Okay, and if I skip the math, okay, I'm going to skip the math because I know that these are fairly straightforward integrals and something that you need to get used to and know. I will obtain s is equal to s0 plus v0 times t minus t0 plus half times ac times t minus t0 whole square. Okay, I'm going to put a box on this as well. This is another equation that I have obtained when you have the constant acceleration situation. Okay. Then I come to the third case here. Okay. In the third case, we have this chain rule that we used. A is v dv by ds. So let me make use of that. Okay, that's going to give me a relationship between velocity and distance traveled. Okay, so I'm going to look at the third situation. And we have A is v dv by ds, which means if I cross multiply, v dv is a times ds, right? Which means that I can say v dv is ac times ds, because acceleration is a constant, which means I can now integrate this. Okay, so this tells me that integral of the expression on the left hand side, which is v dv, starting from an initial velocity v naught to some velocity v at time t, is going to be from s naught to some s ac ds. And something to note here is s naught is the initial distance. Okay, and I'll write that down once I integrate this expression. Left hand side and right hand side, after doing the integration, I'm going to skip the details once again. It's going to give me v square is v naught square plus 2 times ac times s minus s naught. Okay, I'm going to put a box on this again. Okay, and I'm going to collect all of these that I have obtained. Okay, and I'm going to say the following. In summary, okay, for a constant acceleration situation, A is equal to AC is equal to a constant, and for a particle traveling along a rectilinear path, and for rectilinear motion, the following equations hold true. Okay, and these are the ones that we have just boxed, so I'm going to collect all of them. Okay, so I'm going to take this creature here. Okay, I'm going to copy that, and I'm going to paste that here, and then I'm going to get this guy here, this big guy. Okay, I'm going to copy that and bring that here, and lastly I'm going to have this important relationship as well. Okay, so I'm going to copy with your permission and paste it down here. Okay, so these are the three things that I have. V naught is initial velocity, T naught is initial time, and then I can also make a note and say that okay, S naught is initial displacement, and S and V and S are the velocity and displacement at some time t. Okay, so you can think of S naught as initial displacement from some other initial position, perhaps from a reference position, if you want to think of it that way. So initial displacement from a reference position. All right, and V and S are the velocity and displacements, and I'm going to call them as equations 1, 2, and 3. Okay, so this is equation 1, and then this is equation 2, and then this is equation 3. Okay, I'm now going to come back to our problem. Okay, I'm going to copy the figure for our problem from up there, the initial page. Okay, and I'm going to take all of these guys and bring them down. Okay, and then start making use of all of these equations that we have just spent a good amount of hard work deriving. Okay, so back to our problem. What do we have? We have VA, which is the velocity when it starts, right? So this implies that V naught is the same as VA in this case, and that's 4 meters per second. then I also know that the magnitude of the acceleration vector is AC is 0.25 times g, and this is so many meters per second square, where g is equal to 9.8. Okay, and g is 9.8. Okay, the important thing though is this is traveling up the incline, the initial velocity, and the direction of the acceleration is down the incline. Okay, that's a key thing to make note of. Okay, then what do we have? We can say that, okay, I'm initially starting at some time t naught is equal to 0. So let us say we start at some time t naught is equal to 0 seconds. Okay, then I'm also going to say that, okay, hey, I'm going to start at some initial displacement with respect to a reference of 0. So let us say that we start with s naught is equal to 0 seconds, 0 meters as well. Okay, these are seconds and these are in meters. Okay, and then what I'm going to say is, okay, what is the problem asking me? The problem is asking me, hey, find the maximum distance traveled by the ball up the incline. And what is the key statement here? If the ball is going to travel the maximum distance up the incline, then the velocity of the ball at its maximum location is going to be 0. Right? So that's something I'm going to write down. So as the ball travels the maximum distance along the incline, its velocity, when I say ball, I interchange it with particle, so its velocity at the maximum location is 0, which means that I can say, okay, so say S max is the distance traveled from point A to the maximum location, and T max is the time taken to go from S naught to S max. And what we know is that the velocity at t is equal to T max is actually equal to 0. Okay, and if that is the case, then here is what I'm thinking. Okay, I need to find S max. Okay, then I need to find T max. What are the equations I could use? Okay, like go back to my set of equations that we have just written down here. We say, okay, I know the acceleration AC, I know something about the initial velocity, I know something about the velocity at time t is equal to T max. Then I will make use of equation 1 and then obtain the time taken to reach the maximum location. And likewise, if I know the initial velocity v naught, and if I know the acceleration AC, and if I know the final velocity v max at the maximum location, I can make use of equation 3 to find S max, or vice versa, I can use equation 2 as well to find S max. I have innumerable choices here. Okay, so I'm going to make use of equation 1. Okay, so make use of equation 1 to find T is equal to T max. Okay, so from equation 1, here is what we have. V max is V naught plus AC times T max minus T naught. But the important thing is this. So careful. Since ball travels up the incline as we go from T naught is equal to 0 to T max, AC is actually minus 0.25 G. Okay, And so if I do the substitutions now, so V max is equal to V naught minus 0.25 g times T max minus T naught. And I know a couple of things about the maximum velocity, that is going to be 0. Then I know that the time T naught is going to be 0, which means that I can solve for T max, okay, which tells me that T max is V naught divided by 0.25 g, okay, which means that upon solving, T max will end up being 1.63 seconds. Okay, so this is the first piece of good news in this problem. Then the second thing is I need to calculate the maximum distance traveled. I'm going to make use of equation 3. Okay, so use equation 3 or equation 2, your choice, to obtain S max. Okay, so from equation 3, here is what I have. V max square is V naught square plus 2 times AC times S max minus S naught. Start substituting. Once again, my acceleration is negative because I'm traveling up the ramp from S naught to S max. Okay, so once again, AC is minus 0.25 g once again, okay, because we are traveling from S naught to S max. If I'm traveling from S max to S naught, then my acceleration is actually going to be plus 0.25 g because my ball is now traveling down the incline. That's not the case I'm interested in right now. Okay, and so this tells me that V max square is V naught square minus 2 times 0.25 g times S max minus S naught. Cancel off some of the things that you know are 0. This is 0 and this is also 0, and so this tells me that S max is V naught square divided by 2 times 0.25 g, okay, which is approximately going to give us 3.26 meters. Okay, so this is the final answer. And one thing that you also want to notice here is that okay, if they ask you to find the total time taken for the ball to travel from point A, reach the maximum location, and then come back to point A, it's just going to be twice the time T max. Okay, something that I want to make a note, because acceleration is a constant in this problem. The total time taken to go from point A to maximum location and return back to point A, which I'm going to call as T total, and T total is 2 times the time taken to go from the initial to the maximum location in this problem, which is approximately 3.3 seconds. And the key is because of the fact that the acceleration is a constant in this problem. Okay, because of that particular fact, we can say that the total time taken is twice the maximum time to go from T naught to T max. All right, thank you very much.